doesn't help if you guys keep asking questions and want to learn, you know?
Sorry.
So, yeah. All right. There we go. Okay. Oh, there's one more thing. Okay. Oh, no, I forgot the clicker thing. Where is it? Hasn't popped up yet. There it is. It's not the right one, it's fine. Okay, now we can start. So, we were talking on Tuesday about ionic bonding. So we started out understanding where those ion charges come from. Something we looked at in 221, but you know we just kind of looked at it again. You don't have to worry too much about, well, you do have to understand where they come from, but when you think about what is the charge of an ion, just look at the periodic table. Group 1 is +1, group 2 is +2, excuse me. Group 3 is +3, and then we have the anions. They work the same way, they just go backwards. So we went over this, this is review again. We went over the idea that cations are going to be smaller than their neutral counterparts. Anions are going to be bigger than their neutral counterparts. This is a useful knowledge so that you can understand how the ionic bond works in Coulomb's law. And I'm going to just skip through this because we did go over this pretty well, I think. So we want to use Coulomb's law to understand which ionic compounds have the stronger ionic bond. And we ended up picking out when the charges are the same, +1, -1, +1, -1. You have to look at the sizes. These smaller ions are going to create the stronger ionic bond, and therefore they're going to create a higher melting point compound, right? The stronger the ionic bond, the higher the melting point is going to be. So in this case, NaBr. Na is smaller than K+. In addition to melting point, the other thing that correlates with strong ionic bonds is the lattice energy. Lattice energy is just a very specific definition of what kind of an ionic bond strength would be. It is the energy required to separate two ions in an ionic bond and turn them into gas. That's the definition of lattice energy. So really you're just trying to break that ionic bond. So it correlates very well with the strength of an ionic bond. So which one has the larger lattice energy? It's the same one. It's the one that has the stronger ionic bond. NaBr, because Na is smaller. Now, if the charges are different, well, that's what you should be looking at first, because charges play a much greater role in the strength of the ionic bond. So here we have a +2 and -2 charged ions. Their melting points are so much higher than the melting points of the +1 and -1 charged ions that are making an ionic bond. And melting point correlates with ionic bond strength. So yes, charges are the most important. So look to see if they're different charges, and that'll settle it. So between MgO and NaF, don't worry about the sizes, worry about the charges here. MgO +2 -2 is going to have a higher melting point. Yes?
So lattice energy is the amount of energy to turn solid matter. Is it just matter? Is it?
It's an ionic compound. It's to separate the ions in an ionic compound.
To gaseous.
And make them gases, yeah. Yeah. And so part of that definition is breaking the ionic bond, which is what we're kind of focusing on. Right? Okay. And again, this Coulomb's law kind of spells it all out. The larger the charges, the larger this numerator is going to get, and so the greater the force. But if I make the distance larger, this denominator, if this gets larger, then this term gets smaller. So the smaller the force. So larger ions mean a weaker ionic bond. So we want small ions to make a stronger ionic bond. Okay, so we went over this. KCl stronger, higher melting point because of the smaller K plus versus cesium plus. And we did this one as well. Oxide versus carbonate. These are both -2 charged ions. So carbonate is a bigger ion. I mean, you can physically see it. It's carbon with 3 oxygens versus just a single oxide. Okay, so that's stronger bond, higher melting point. All right, so that's kind of what we went over already. And we're going to move on to talking about metals specifically. And if we're going to talk about metals, let's compare them to nonmetals, just to kind of compare and see what makes metal special. Metals are shiny, they are malleable, so that's the word we use to describe that we can pound them flat, make sheets, foil, whatever. They are ductile. That means you can stretch them into wires. They stretch, they don't break, or they can, but you can make them stretch. And most importantly, they can conduct heat and electricity very, very well. So we're going to get into a little bit into what electricity is, but really electricity, as long as there are mobile charges, that's what causes current in electrical circuits. If you've got any kind of flowing charges, that's a current, and that's electricity. So we're looking for mobile charges. That's what makes something conductive. By contrast, nonmetals actually have very indistinct properties. They're kind of all over the place. Sulfur is like this yellowish, crumbly substance. Oxygen's an invisible gas. Bromine is this brownish liquid. They've got lots of different properties. They've got lots of different types of bonding and structure. Some of them are molecular. They make they're mostly molecular. Anyway. But what makes them very different from metals is their electronegativities. Their ability to attract electrons, specifically shared electrons, but in general, nonmetals attract electrons a lot more than metals do. Right? So they have a high electronegativity. So we're going to start this section, Chem Activity 23. We've got this little chart here. It has a list of different chemicals. And I think we're going to skip this because this one's a little bit too simplistic. Do you guys actually have copies? Does anybody not have these yet? Okay. We'll do the first one on the board. Anybody else? Okay. So, in order to answer some of these questions, you're going to need the electronegativity table from the workbook. This is a little different than the one that Linus Pauling created. That's the more common one that you see online. Let me switch masks. I can't breathe well enough through this one. Okay, so the one that's more common, that's all over the internet, that's in the Mastering Chemistry textbook, is one that has fluorine as the top right element on the electronegativity table. And in most of those tables, fluorine is exactly 4. This one's a little different. It actually includes the noble gases. Don't let that throw you off. Just remember that electronegativity is not a measured value. This is not something you can directly measure. Electronegativity is a calculated thing that is just a determination of how attracted to electrons are these things. And there's a couple different ways to try to calculate this, which is why you get different tables. So for some obscure reason, this textbook uses its own version. So when you get questions from this workbook about electronegativity, try to use the table that is listed here. And I think I can, I think it's in your appendix, but I can put it on D2L separately too. I'll have to remember to do that.
On the last page of the draft recording.
There it is, yeah, last page. Okay. So, yeah. So model 2 of this same thing. Yeah, the first couple questions are a little bit too simple. Oh, no. Anyway, we're going to do all of it together. So model 2 switches from looking at metals versus nonmetals to looking at the difference between ionic and covalent bonding and metallic bonding. Okay, so first let's look at ionic and covalent bonds. We've studied them. Covalent bonds we did in 221. And in covalent bonds, you are sharing electrons between a pair of atoms. Those electrons are shared by the orbitals of those two atoms overlapping, and that's kind of where those electrons exist. They exist in those orbitals that these two atoms are sharing. Those electrons are localized. They are between those two atoms. That's where they are. That's what it means to have localized electrons. In an ionic bond, so for instance, sodium and chlorine, sodium will transfer an electron to chlorine to make sodium plus and Cl minus. We still know where the electron is. The electron is now on the chlorine. It's a chloride. And so the electron is localized to the chloride. So in both of these kinds of bonds, even though they're very different kinds of bonds, they are localized electrons. We know where the electrons are. Now there is a version of covalent bonding where it's delocalized. We saw that in 221, pi bonds and stuff, but we're going to ignore that for a second. But in metals, it's very, very different kind of bonding. So the electrons are delocalized, meaning the electrons are free to move around wherever they want in the metal substance. So how does that work? Well, the way you should think about metallic bonding is that the metals, first of all, they're all neutral. Even though you see these positive charges here, remember that metals, when you talk about iron metal, or titanium metal, or nickel metal, you're talking about the neutral atoms. So these atoms are all neutral. But the way you should think of it is the valence electrons on these atoms are really loosely held. Right? Metals have low electronegativity. They're not super attracted to their own electrons even. And so those valence electrons are loose. So if those electrons were to temporarily leave, what would you have left behind? You'd have left behind a cation, right? So think of a metal as being a bunch of cations in fixed position, right? Most metals are solid. But then there is a sea of electrons floating around that can go wherever they want. And if you think about, well, what about conductivity? Well, we'll get to that in a second. So let's answer these questions. 1 through 8, starting from the beginning. And I'm going to give you a chance to think about these before I spoil it for you. So, chem activity 23, 1 through 8. Take a few minutes to do that. So if you're just, well, so the table's written a little bit confusingly. They're showing the elemental form of oxygen, which is O2, but the electronegativity is for one oxygen. Yeah, so a single oxygen atom has an electronegativity of 3.61. Yeah. Oh, excuse me. Okay, let's talk about some of the answers since you had a chance to go through it. The way we're going to be thinking about these is going to kind of hopefully guide how we think about the future sections here, okay? So, number one, what kind of bonding is present in the nonmetals? Covalent. All right, that's easy. Nope, that works. But how do you know? Like, what evidence do we know that these are covalently bonded?
Because they're sharing the electrons.
Why are they sharing electrons? What in this table tells us they're sharing electrons?
Because they're higher electronegativity.
High electronegativity, yeah, perfect. So high electronegativity, if you've got two oxygens, which one's going to take the electrons? Well, they both want them, so they'll share. Okay? So high electronegativity means they have to share them. They both want electrons, they're going to share them. Okay. 2A, how do you know that it's not ionic bonding for the metals? We can use our intro chem definition, right? What do ionic bonds normally?
Not a metal and non-metal.
Metal and a non-metal, but electronegativity-wise, why do metals not do ionic bonding?
Because they're low electronegativity.
They're low electronegativity, and to do ionic bonding, one of them has to be an anion, right? So one of them has to really want an electron. So if you have two metals that are both low electronegativity, one's not going to steal the electron from the other, because neither metal really cares about having an extra electron. So that's one reason, or that's the reason. And we know that they don't exhibit covalent bonding for the same reason. They both low electronegativity. Non-metals like to have a full octet. The metals normally don't care as much. They don't need that extra electron, so they're not going to do the sharing, at least not in the way that covalent bonds are sharing electrons. Okay? So it all has to do with electronegativity. We're going to be focused on electronegativity for the next couple sections. It's going to be the key to most of the answers. All right, 3. That's kind of, we went over this, is the description of metals being comprised of atoms with loosely held electrons consistent with the data in table 1. Well, everything has low electronegativities in table 1, all the metals do. So yeah, they don't really care about their electrons as much. They're not attracted to their own electrons very much. So yeah, sure. Considering that electricity is a flow of electrons from one place to another, propose an explanation for why metals are generally good conductors, whereas covalently bonded compounds are not. So if this is really a metal, these electrons are loose. They can go where they need to go. And so all you got to do is, in physics or in electricity, you apply a potential. You apply a positive charge to one side, a negative charge to the other side. You cause the electrons to move to that direction or to the positive side. I mean, that's more physics than anything else. So the electrons are free to go, free to move. That's the flow of electricity. That's what causes the flow of electricity. And it doesn't have to be electrons. It can be anything that's charged will create a current, is electricity. It doesn't have to be electrons. Electrons are charged, which is why we use electrons often, but it can be ions too. We'll get to that. So, based on the data in Table 1, explain how the electronegativity of an element can be used to predict whether the pure substance will be a metal or a nonmetal. So, I mean, just looking at the table here, they're telling us metal, nonmetal, but if we look at the electronegativities, there's kind of a border. So, around 2 is where they flip. I mean, it's not clear, we don't have that many examples, but you know, something below 1.8, 1.9 maybe, something above 2.3 or 2.2, something like that, is a nonmetal. So we can kind of look at the electronegativity only just to kind of gauge whether something is a non-metal or metal. That's it. What else we have? We're doing up to 8, right? Yeah. Okay. Number 6. All of the electronegativities in table 2 are fairly grouped close together. There we go. Which element's electronegativity is the exception? Arsenic is kind of close to tellurium. It's kind of within there. What about this one? Aluminum, 1.6 is kind of a little bit out there on its own. The next one after 1.6 is like 1.92, so that's a big gap there. So aluminum is by itself. And hopefully that kind of rings some bells, because look at what these are. Aluminum is a metal. The rest of them are what we call the metalloids or semi-metals, right? Probably don't recognize them because we don't use them ever, but the rest of them are the metalloids, the ones on the diagonal line. So just to remind you, on the periodic table, everything on the diagonal line is a semi-metal or metalloid, except for aluminum. Aluminum is still a metal. And it is, right? It's aluminum foil is a metal. It's shiny, it's conductive. We used to use it in house wiring until, I mean, it's not very good for that. If you have an old house, they want to rip it out, but some old houses still have it. All right. I think 7, I forgot. Maybe I couldn't find it. All of the electronegativities in table 2 have electronegativities in the range of 2.06 to, sorry, this is making noise, to plus or minus 0.15. So 2.06 plus or minus 0.15, that range basically means 1.91 all the way to 2.21. Right, so that's the range they're talking about. What are all the other elements with electronegativities in this range? And I think they were all up there. I don't know if there is any missing. I don't know if you can see any. I think they're all up there. Alright, if you see any others, let me know, but I think they were all up there. It's pretty much just going to be the semimetals that fit in that range. And then the last one, so here's a paragraph. Feel free to read this at home. And this paragraph basically says, yeah, anything that falls within this range for electronegativity can be considered a semimetal or metalloid. They have properties in between metals and nonmetals. Silicon is shiny, but it's not conductive, or at least not normally. Now, we're going to spend a lot of time talking about the semimetals a little bit later, and semiconductors, but we'll table that for now, okay? And this last question is basically is saying, well, a student is saying you can find the semimetals using that dividing line. The line has to be diagonal. Why must it be diagonal? Well, I think this is either too obvious or too weird a question, but if we're using electronegativity to gauge whether something is a semi-metal, well, what is the trend of electronegativities? Fluorine is the highest, so up and to the left, or to the right, excuse me, is the highest. Down and to the left are the lowest. So if the electronegativities kind of go up on a diagonal basis, then that middle ground where that range falls is going to happen along this diagonal this way. That's it. That's all they're trying to make you see. Just getting really familiar with the periodic table. Okay. So this is a little bit of an intro to the next topic. Understanding how to think about elements and their properties via electronegativities. So let's switch gears. Oh, before we do that, let's talk about bonding. So if you were talking about covalently bonded substances, this is not working. Oh yes, it is. How would you describe the electronegativity of the elements in any generic covalently bonded substance? Would you say they're low on average, intermediate, high on average, or just variable? And just based on what we know. Good. So, I can understand B, but in general, it's high. Okay, we're talking about nonmetals generally making covalent bonds, and the nonmetals are higher than 2.2, right? So they're 2.3 to 4. So we're talking about on the high end. Yeah, hydrogen's a little low, 2.1, but most of the other ones are higher than this. So high on average, let's put it that way. Okay. Yeah, there we go, higher than average. And if you talk about metallic bonding, take any two metals. What kind of bonding, like what would you describe the electronegativity of those metallic substances? How would you describe the electronegativity of those substances? That's what I wanted to say. All right. So I think intermediate is not a generous one in this case. Well, that would be generous, I should say. They are low on average. Electric metals have generally very low electronegativity. And I know you guys aren't familiar with it because we don't really talk about that. But something like sodium, I think, is like 0.7. They're all really, really low. The transition metals are weird, so don't worry about those right now, but metals generally have low electronegativity. So if I put any two metals together, they'll, on average, the electronegativity will be low. And here is the kind of linchpin of this idea. If I talk about an ionically bonded substance, how would I describe the electronegativity of the elements in an ionically bonded substance? Okay, I think people are getting it. Oh, so variable kind of, in the sense that, yeah, you're pairing a metal and a non-metal, and they're very different. But if I average them out, a low with a high, they'll average out to somewhere in the middle. And so we're going for is, yeah, intermediate, like middle range electronegativity on average. So this is going to be a key part of understanding bonding, is knowing how to describe the bonding using an average of electronegativity. This is going to be one of the key measures we're going to use. So we're going to start to look at properties of compounds. We're going to use, not yet, but we're going to develop something called a bond type triangle, which is going to be kind of a graph that will help us understand what kind of bonding we're going to see for any two elements. So we're going to switch from thinking of metal, non-metal as ionic, non-metal, non-metal as covalent, to a more gray area kind of bonding, okay? So, why would we want to know about what kind of bonding something has? You know, why is that so important? I mean, it's not just nomenclature, it's also understanding the properties. So this next week's lab is going to be all about understanding the properties of the different kinds of substances. So here's just a preview. With ionic bonds, ionic compounds generally have high melting points. Anything over 500, they can go up to 2,000, 3,000 almost degrees C. They are generally brittle, hard but brittle, so you can take a hammer and smash an ionic compound pretty easily usually. And they're not conductive. The only time the ionic compounds are conductive is if you melt them. Why would they be conductive when you melt them?
Because the electrons are loose.
Not the electrons. So think about a solid like sodium chloride. Sodium chloride is a bunch of sodium ions and chloride ions in this pattern, and this is two-dimensional, so imagine 3D, but they're locked in place as a solid. But when you melt something, what happens to the atoms when it's a liquid? They move around now. So you've got mobile charges now. And that's the condition for conductivity, is charges that can move around. So once you melt an ionic compound, that molten salt will be conductive. In fact, that's how I think that's still how they generate chlorine gas, is they melt molten salt and then stick electrodes into it and run a voltage and cause the chlorine to turn back into the chloride to turn back into chlorine gas. And then they get sodium out of it too, but yeah. So, ionic bonds have those properties. Metals, they're variable melting. Some can be very low. We saw gallium in lab. Mercury is already a liquid at room temperature. Some of them are really high. Tungsten is like one of the highest melting point metals ever. Tungsten is W on the periodic table. There it is, 74. The other name is Wolfram, that's why it's W. It's German, I think. Anyway, I don't know why we called it tungsten, but that's what we call it. Sodium, Na. Some people call it natrium, which is why it's Na. All right. And that's different from the aluminium thing. That's different. That's marketing. All right. The melting points are really variable. It really depends on a lot of things, which we're not going to get into too much right now. But here you can see sodium has a low melting point. Magnesium's higher. Here's vanadium, pretty high. These are all metals, so pretty variable. The other class are the covalent bonds, compounds with covalent bonds. And this is also another category that is really variable. Some things are really low melting point. Water is already a liquid. Oxygen is a gas, O2. There are variable hardness. So sugar, you can take a sugar cube and smash it to pieces and grind it to powder very easily. But diamond, which is a covalent compound as well, is the hardest thing on Earth, right? So variable hardness. What covalent compounds do almost 100% is not conduct electricity. These are what are known as insulators. They don't really conduct electricity at all. There are some exceptions. Graphite, which is another form of carbon, does conduct electricity, but it's a special case. So next week's lab will focus on kind of examining all these different properties. It's kind of a fun lab again. All right. Now, we're going to go through Chem Activity 24, and it starts off with this table, that is not quite filled. So notice that it has the electronegativity of the two different atoms that are involved in a compound. If it's a metal, it's just going to take the electronegativity of two different cesiums, for instance. And we calculate the average electronegativity. All right, in math, when you do a bar across something, that usually means mean, similar to average. So you add the two, divide by 2. And then this is the difference in electronegativity. So one subtracted from the other, absolute value. We have your melting point, just so you can see what the properties are. And we've got type of bonding listed here. Here it's unknown. You're going to figure it out yourself. So let's do questions 1 through, it should be 1 through 3. 3 is in 3 different parts. But let's do questions 1 through 3. Take some time to fill out this table and understand what kind of bonding we're going to have for these things. Okay? Be right back. Yeah, that's okay.
Sure, the distance between the range
Yeah, so after this should look like that. So that comes next. That's it right there. So yeah, you just That's okay. You're getting ahead with the homework, that's all. All right. I think we've had a chance to answer a few of these. So for ranges, you're just picking the minimum and maximum for that category for each of these average electronegativity and change in electronegativity. Now, don't forget that this is just a very small sampling of compounds. We've only got 3 in each category. So these ranges are not hard and fast. It's not like a rule, okay? It's approximately where we find these. So let's look at, question 2 was determine the values for average electronegativity and change in electronegativity for HI and gallium arsenide. Hopefully everybody got that right. It's not too hard to figure out. But if you got it wrong, let me know so we can fix what's wrong with your calculation. Now 3 is the critical ones. So let's kind of categorize where does HI fall. And if we did it with the introchem method, nonmetal, covalent. Well, let's confirm. 2.33 doesn't quite fall into it, but again, remember this is flexible. It's not exactly going to end here, so maybe 2.33 falls within this range. It does fall in the ionic range too, not at all for metallic. But for the change in electronegativity, 0.006, it definitely falls here under the covalent range, not at all in ionic. So HI is pretty clearly covalent. There's a tiny bit of wiggle room because it's not exactly in this correct range here, but it's pretty covalent. Now gallium arsenide, this is the interesting one. If we went with our black and white thinking, gallium is a metal, arsenic is a semi-metal, but we tend to have treated semi-metals a little bit like non-metals when it comes to nomenclature. So maybe ionic, but let's see what the numbers say. 1.99 for mean. That falls pretty well here. Maybe it's on the verge of being metallic here, but better ionic. And then 0.45 for the difference in electronegativity. Well, it doesn't fit in the ionic category here at all. It doesn't quite fit in the metallic category either, or covalent. So this is one where it's kind of hard to tell what kind of bonding it does just from this chart. Maybe metallic, maybe ionic. It's hard to say. Yeah, so ionic, metallic maybe. It's unclear, okay? And if we look at the last one, silicon. Well, that's a semi-metal. So how does a semi-metal bond with a semi-metal? What kind of bond is it? Well, according to the data, 1.92. Ionic, maybe? For average electronegativity, but it doesn't fit the change in electronegativity at all. That fits over here, metallic or covalent. It's not even on the map at all. Silicon is none of these. Maybe all 3. Maybe, who knows? It doesn't fit in any one of these. So this is kind of not proof, but it's evidence that supports this idea that shoehorning things into a specific category is not really the way to think of bonding in general. We need to start being a little bit more flexible in how we treat the interaction between 2 atoms and understanding how to think of that bond. Okay. So this is where the bond type triangle comes in. Oh, and I guess yeah. So we did this. HI is best classified as covalent. gallium arsenide is not really any one specific one. It's kind of, I think we said metallic covalent? No, metallic ionic. Yeah. Anyway, it's hard to tell. And we didn't do sulfur here. So this is where the bond type triangle comes in. This is going to be a tool that's going to help us, again, understand better what kind of bonding we're looking at. And again, this is not a rule. This is not, hey, it falls here, it's definitely this. This is, again, a guide for understanding what kind of bonding we're looking at. So, this is using data that we're already familiar with. We have the average electronegativity on the x-axis. We've got change in electronegativity on the y-axis. And so let's start just by going through questions 6 through 10. Just kind of getting comfortable with looking at this triangle and understanding what we can get from it. So, 6 through 10. Actually, before you guys keep going any further, let's do the first question together. So, CS is one corner of the triangle, cesium fluoride another corner, F2 another corner. Why would they pick these to be the corners of the triangle? Anybody want to have a go at suggesting why?
The lowest and highest.
Yeah, the highest and lowest electronegativities when it comes to things that do bonds. I mean, yes, noble gases might be higher, helium, but they don't really do bonds, so we're going to ignore them. So yeah, we're looking at the extremes of electronegativity, lowest and highest. So those are going to define our boundaries. All right, so keep going. Sorry. Yeah.
Sorry to ask this, but how do we calculate, I got this wrong, how do we calculate the EM Yeah, yeah, so just look at one bond at a time, so a C A bond, and that's it, that's all you have to consider. Yep.
Oh, that's actually there, so I would just do C plus H times 2 for that.
Yeah, yeah, right, yeah, there's 4 bonds in there, but one bond is just a C with an H together.
think we can talk about some of the answers maybe. So I think we covered question 6, but question 7 is just plotting where these different substances appear on the bond type triangle. That one looks like sodium chloride. Make sure you get the right average and the change. This one is the next one. This is sodium metal. That is methane. And somebody asked a question about how they calculated the change in electronegativity and the average when there's 4 or 5 atoms. We're only looking at one type of bond, so a CH bond. You just kind of focus on just the one bond and that's it. And then this is the last one, silicon. And so question 8, associate these regions with the bond types. So you can kind of tell from like what the corners are. But, you know, this thing that we put a dot here for is for sodium chloride. And so this region represents the ionic compounds. All right? This is an ionic compound. This is the most extreme case. Very low electronegativity metal, very high electronegativity nonmetal. But anything in this A region is considered to be ionic. B would be the metals, because we have a sodium in here, plus cesium is the most extreme. C, covalent. We've got a methane. We've got the most extreme covalent compound, F2, on this corner. So, and last but not least, this area here, this is a special area. This is semi-metals. And this is where silicon falls. It's kind of one of those weird bonding types that doesn't really fit in anything else. On an exam or a quiz, you will get this graph with no labels. Like, so this will be here, that'll be here, and the numbers will be there, but you won't have cesium, you won't have cesium chloride or F2, and these won't be labeled at all. You'll be expected to know what the regions are yourself. And you can figure it out from what should a metal have for change in electronegativity? What should a metal have for average electronegativity? And so you know metals are low, so you can figure it out, okay? Now, 9. Let's kind of figure out the bonding for HI and gallium arsenide. So HI was 2.33.06. Let me try a different color if I can. Maybe blue. Let's see if that works. 2.33.06. That's there, right around there. 0.06. 0.06. Yeah, so barely above the line. Kind of right there. Oh, it's doing that thing again. Ignore the little streak. So that's pretty. I mean, that's pretty much in covalent. We assume that, but I mean, notice it's getting close to the border. You're getting to, you know, HI. While we can consider it covalent, we could also say it has significant metallic character. It's close to the metallic side. All right, definitely more metallic character than F2 would. Okay, so we're going to be talking about degrees of bonding in this case, mostly. You can definitely categorize things, but when you compare two different compounds, you can say that this has less covalent character, more covalent character. You can say things like that now. Now gallium arsenide, 1.99, 0.45. That one is 1.99, 0.45. It's kind of right on the border. So it's in the semi-metal region, but a little bit in the covalent region. Pretty much in the semi-metal region. So we basically have this compound that is made of a metal and a semi-metal, but it's kind of acting like semi-metallic bonding. It's like silicon bonding. So why would we want to know this? Well, it turns out that gallium arsenide is pretty much in every single red LED you've ever seen. That's the material that makes red light in red LEDs, is gallium arsenide. And LEDs require semiconductors to work, so it definitely has semiconductor-like properties, okay? Now, if anything is right on the line, it's pretty clear. You can categorize them as both. If they're close to that line, you can still categorize them as both. You can say it's covalent with significant ionic character or something like that. On an exam or a quiz, if there is a blank space where you can describe the bonding, please be thorough. You know, I might disagree with you, but if you say why you picked that, then I'll give you full credit. For the multiple choice ones where it's just one answer or the other, I'll try to be very clear. Like, it'll be not interpretable, let's put it that way, okay? And if you disagree with me, bring it up, please. All right. Oh, I think we have one more. Let's see. There it is. Quartz, silicon dioxide, is a very high melting hard solid. Place a point for silicon dioxide on the bond type triangle. What type of bonding? So, for silicon dioxide, we need to calculate these two values, the difference in electronegativity and the average electronegativity. Did anybody do that?
Yeah.
Yeah, what do you have for average?
2.765.
1.7.
No, 2.7. Sorry, 2.77.
Okay. And for difference?
1.69.
Thank you. So if we plot those, 2.7, right around there, 1.69, right around there. So, you know, this is definitely in the covalent region, getting close to ionic. And what makes that interesting is because it's like that, you get this. Like, you get structures that are, I mean, they're not molecular, where they're like little pieces that just little molecules that can be separated very easily, and they're not ionic, where you have these ions, and you know, like salts, you can crush them very easily. You get this thing, which is what we call a covalent network, which is like what diamond is. It's these covalent bonds that just keep going. Like this is basically one giant molecule, basically, and that's quartz. So I forgot to show this to you guys earlier, but I've got a couple of examples of nonmetals. There's some sulfur. Here's sugar. That's big wow. We've got a lot of metals here. Big block of lead. It's nice and heavy. And the metals are conductive. So this is a conductivity tester. There we go. And there's your gallium arsenide LED, the red one. Aluminum, conductive. This is silver on the inside of a flask. There's some iron, all conductive. So silicon, this is silicon. It looks like a metal, shiny, and it's heavy like a metal, but it shouldn't be conductive. It's weakly conductive. I don't know if you guys can see it. It's lighting up, but only one light, or maybe barely the second one. If it was really conductive, all of the lights would be on and be louder. Semiconductors are generally, this shouldn't be that conductive, are generally non-conductive until you give them energy. So if you heat them up, suddenly they'll become conductive. And that's, if you know anything about electronics, that's a switch. It is a condition for turning something on or off. Like, you give it energy, it's suddenly conductive. And you take away the energy, it's not conductive anymore. So that's used in computer transistors. Like, that's the purpose. And plenty more other reasons. Plenty other areas. So feel free to play with these if you like. But that's some ionic compounds there. All right, so let's go through some more questions using this bond type triangle. And I apologize, the font is tiny. This is the best we can do to fit everything in here. So we've got a bunch of stuff listed here. We'll ask you some questions. But they've been kind of highlighted. Oh, by the way, ionic, metallic, covalent, semi-metallic. We covered this, so bonding is, oh, sorry, we didn't do this. So, which best, you've seen the answer, but which best describes, I thought it was a different question, which best describes the bonding in metals? So, we already know that they're not high, they're not intermediate, they're low electronegativity, so that's not on here. But the other two answers are localized electrons or delocalized electrons. So metals have the delocalized electrons. And that's what causes them to be conductive.
I think it means the D.
Yeah. Yeah. All right. This is not bond type triangle. This is going back a little bit. But if you were to rank these in order of increasing lattice energy, which one is the answer? This is kind of what the homework due on Tuesday is. So lattice energy is directly proportional to the strength of the ionic bond. Right. So we've got most votes for B, and the answer is B. Yep, there we go. In this case, if the charges are all the same, magnesium's +2, strontium +2, beryllium +2, the fluorines are all the same. They're all -1. So we can't compare by charges. They're all the same. So we compare by size. And strontium is the biggest of the group 2 ions in this particular set. Magnesium is next. Beryllium is the smallest as you go from bottom to top on the periodic table. So the smallest ions will create the strongest bond, and thus the largest lattice energy. Will require the most energy to break them apart. Okay, here we go back to the bond type triangle. So, which of these covalent compounds, and these are all here listed in this oval, has the greatest ionic character? So again, that's a way of just saying this one's more ionic than something else. They might not necessarily be ionic. In fact, they're all in the covalent side. Okay. So, you guys said E, yes, you'd be right. All right, this is easy, right? Okay. By the way, silicon carbide, I think, is what they used to make tool tips out of. It's just hard. It's cheaper than using pure diamond.
Just
A little cheaper. Probably easy to work with too. But yeah, it's closest to the ionic side. The ionic side is up here. It is the closest to it, so it is has the most ionic character. We can even get down to the nitty-gritty. We're not going to do it in this class, but you can even describe covalent character, ionic character using percentages even. We don't have to do that, but that's how detailed you can get when you describe bonding. So here we go. Which one of these has approximately 50-50 ionic covalent bonding? And these are in circles. These are the small circles. All right. You guys are on fire. Good. I'm glad this is so easy. Everybody's going to get 100% next week on the quiz, right? Okay. So yeah, that aluminum chloride, which by our intro chem reckoning is ionic, right? Metal, non-metal. That's what we'd think. But really, it straddles the boundary. It's part ionic, part covalent, which is unusual. We wouldn't expect that, but it really is. So what would that mean, that it's a little bit covalent? Well, ionic compounds make these network structures where they're just repeating aluminum ions with chloride ions. Maybe you can find molecular aluminum chloride. Maybe that's what it means. Actually not too familiar with this one, but that's kind of why you would want to know this. You can kind of predict the properties. Okay, use the bond type triangle. Rank them in order of increasing covalent character. These are the boxed ones. This you could do without the triangle, I think. But it's helpful. The boxed ones across the bottom there, not the one at the top there. Yeah, these three. Yeah, the font's so small. Imagine doing this on Zoom. All right. So, oh, I didn't even show you guys the answer. So most of you got it right. D. Most covalent character, CCl4. It's the one that's going to be closest to the covalent side. It actually is in the covalent side, but it is furthest to the right. This is silicon hydride. I think that's what you would call it. But, you know, it's covalent technically, but it's really close to semimetallic. So it's going to have kind of mixed properties. This thing is not even a covalent compound. It's metallic, but we could still say it has some covalent character. Okay? But it's got the least. There we go. Okay, how would we describe the bonding in calcium hydride? That's the other box that we haven't used yet. Alright. So, everybody says E, and you'd be correct. So, good. I had some people last class say, oh, it's on this side of the line, so I'm going to say ionic. But it would be incorrect to say pure ionic, okay? So, yes, you could say ionic mostly, or a little bit more ionic than anything else. But it's significant amount of both, ionic and metallic. This stuff in real life is really weird looking. It's like this dark gray powder. Kind of looks almost metallic, but not quite. It's not really ionic either. You don't ever find it in crystalline form. Some weird stuff. It's super reactive. They use it in organic chemistry to add hydrogens to double bonds and other things. So that's it for this slide set. I'm going to switch to the next one. Anybody have any questions about the bond type triangle? I think it's pretty self-explanatory. We're going to use it a lot. So keep it in mind.
And it'll always be provided.
I will give you like the outline with the triangle and the lines, but then no labels. Yeah. All right. So let's skip that for a second. So we're going to move on, and we're going to talk about something we looked at in the lab today. Not today, last time. And that was like the structure of solids. We looked at the structure of some metals, iron, and zinc on iron, the galvanized iron. We saw with the demo with the BBs how atoms pack together and make these crystal grains. So we're going to kind of, in detail, look at the structure of solids. What do they do at the atomic level? So when we represent the structure of molecules, like covalent compounds, it's pretty simple. I mean, not simple, but like we've got a very well-established framework, like Lewis structures. We show how the atoms are connected, done. If we want a little bit more detail, we can kind of use VSEPR theory to understand the shapes. So 3D shapes, tetrahedral versus trigonal planar versus trigonal pyramidal, things like that. And if we want to describe the bonding, how we get these angles, we can use hybrid orbitals. So I don't know if everybody remembers, to make tetrahedral shapes, you do sp3 hybrid orbitals. You mix the s and the p orbitals together. Anyway, that's with covalent compounds. So how do we describe the structure of ionic compounds and metallic compounds? And up until now, we've just been kind of hand-waving. I mean, I think I did a picture of alternating sodiums and chlorines in a 2D structure that you just imagine as 3D too. So let's get to a formalized understanding of how to describe these structures. And these are both ionic compounds and metals have these symmetrical extended arrays. So they're both crystalline. They both have these repeating patterns for the atoms. So why? Why do we want to know about this? Well, sometimes the identity of the substance is all that matters when we talk about the reactivity and stuff. But sometimes the structure has a huge role. So we do need to know about the structure. There's solids all around us. This is what Carlsbad Cavern. Here is Mexico's Cave of Crystals. I haven't been to any one of these. These are pretty pictures. Here's a smaller version. These are snowflakes. You can see your own at the snowcrystals.com. I think this website still works. So they say no single snowflake is the same, sort of, but they all have characteristics that are the same. And that 6 point is very, very common. So how are we going to describe these structures, these extended arrays of atoms for metals and for ionic compounds? But let's start with metals since it's a little easier. So we're going to make things simple. We're going to treat all atoms as just spheres, solid spheres, kind of like ball bearings, just to make it simple. And they pack together to form a solid. We are going to describe each atom as having a certain number of nearest neighbors. Basically, how many atoms, how many neighboring atoms are directly touching that one atom. And this is going to range depending on, this is going to vary, I should say, depending on how the atoms pack together. So depending on the pattern that they take. So it could be as low as 6. And we've done 6. That's the octahedral shape. I don't know if you guys remember that from 221. But you can go up to 8 or 12 atoms that are surrounding a single atom, that are nearest neighbors, okay? You have to remember that even though we're talking about a couple atoms at a time, just to kind of talk about the structure, these are macroscopic arrays. Like they extend for many, 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 many atoms, 1 gram is going to have 10 to the 23 atoms. So don't forget, if we're dealing with metals, metals have few valence electrons on average. Sodium, potassium, calcium, they have 1 or 2 valence electrons, and that's it. Aluminum, 3. We're going to kind of ignore the transition metals once again. They're so little special. They make things more complicated, so let's simplify things and ignore them for a little while. Or at least pretend they're just like the others. So few valence electrons for bonding. And metals, we know, have a low electronegativity. So those electrons are loosely held. Okay, so these are the postulates. This is what we're going to assume is always true for any kind of metallic structures. And I don't want you guys to do this, but I'm going to give you this page. Anybody? I think you're the only one that doesn't have it. So if you look at Chem Activity 24A, critical thinking questions 1 through 4, those questions are basically what answered here. So what is the range of nearest neighbors for metal atoms packed into a solid? Here, I'll just flip to it right now. If you guys want to fill it in yourself. I feel like it's a little bit insulting your intelligence, but at least you'll have it there.
What page is it?
So the top page is, oh geez, they're all different. Hold on a second. I've discovered that the page numbers that I have don't match what you guys have. It's somewhere around page 30, maybe it's 34 for you guys. 26, 4 minus, sorry, okay. The new publisher made the pages different now, so sorry. I need to get a copy that you guys have. So these are the questions I was referring to. The range of number of nearest neighbors for metal atoms, 6 to 12. Choose the correct where metals have few electrons available for bonding. Metal electrons are held weakly. And the last part, and this is requires you to kind of read this model here. What is the model we use to represent large collections of atoms at the atomic scale? So model 1 paragraph right here, a repeating building block or a unit cell used to represent extended structures. That's what we're going to do. We're going to understand what unit cells are. And ultimately what they are is the smallest possible kind of piece of that repeating pattern that you can use like as a stamp almost. If you just use it over and over and over, it repeats that pattern exactly. And so you, instead of having to draw the whole thing, you can draw one unit cell and then you know how to draw the rest of it basically. A unit cell has a few requirements. It has to repeat adjacent exactly, so like you can't just move it and leave a gap between the next one and say, oh, it's the same pattern. We'll get into the requirements in a second. So, yeah, we've covered this. So unit cells. These are repeating building blocks used to represent extended structures. And we're going to start with 2D, just to make things a little simple. And then after that, we'll move to 3D. So actually, it's a lot easier in 2D. So this pattern here is in your worksheet. And and this pattern is as well. So we're going to look at questions 5 through 12. Actually, why don't you guys do that? 5 through 12. Spend some 5 minutes looking at these patterns, just kind of understanding what you're seeing and how to recognize what is a valid unit cell and what's not. Especially the next page, just those questions. I'm going to be honest, this is either going to be incredibly easy for some of you, or it'll be like take a few minutes to for it to click. Some people are visual learners, some people aren't, so. No, I've got the wrong one. No, we just have the old publisher pages numbers, so just page 27.
Oh, I'm sorry.
Yeah.
Okay.
Yeah. I have to go through all my slides and change everything. So.
So do the unit cells have to have vertexes inside of the atom?
Nope. The only requirement is that when you move that box that you draw, it has to be directly adjacent to the next one and has to repeat exactly the pattern of the previous one.
So to this one?
Yeah, that's it. Draw a little more carefully, but yeah.
Okay, not on the atomic scale.
So, I'll admit, when you do 2D unit cells, there's a lot more options. When you get to 3D, you're limited in what you can draw.
Oh, that's fair.
So you'll see when we get to it. Yeah, so every one of those boxes you're drawing is the same as the box in the middle.
Right.
And so as long as what's in those is exactly the same as the previous pattern, it's a valid unit cell. And the other requirement is that you don't put any gaps, so like they have to be touching the previous unit cell, right? Okay. Yeah, so it's just verifying, that's it.
Well, you can actually parallelogram.
What's that?
I guess that doesn't work, or that does work.
You can do funny shapes, yep, as long as
It
you can
works.
fill the entire page with them, yeah.
Repeatable, where like they
Yes.
all look. Oh.
Yes, one of them is not.
Would A not potentially and replicate this seems to get sent out to B, so that's all the
Well,
same.
so A has the atom in every corner.
Yeah.
And if you draw the box here, you still have an atom in every
So
corner.
that doesn't matter, like it's out of a like dimension or like setting them up properly, like E, it just as long as they have the full atom.
Yeah, and when you draw them, if you fill this page, there's no gaps. As long as there's no gaps.
Oh, okay.
You
So then
can't have like.
so then B wouldn't be because it's not touching the atoms on the.
Well, no, no gaps between unit cells. So like you can't draw.
The signs need to be meshed together.
Yeah, no. It's so like I guess F. So if I draw a box around here, there's a black atom inside of it.
Oh,
And if I move the box over this one, I'm leaving a huge gap between
Okay,
that box and
that
that
makes
box.
sense.
But that white atom is not the same as that black atom. These are not
Okay.
valid.
That makes
So-
sense.
These and of course the one. So that is or is not, but it's like E, right?
Mhm. Yep. Yep. You can make parallelograms. Yep. Generic parallelograms. Okay. We're okay. We're okay. So, I forgot. So, people were asking me about the top one. What about the bottom ones? CTQ 11 and 12. Does any of them not work? This one down here, yeah. So you might think, oh, well, if I just flip it over, but you can't do that. It has to be exactly the same as you draw. So if I draw the next one down here, it's a white atom on top, black atom on the bottom, which is not the same as that one. All right. So that's not a valid unit cell, but the rest of them are. And you can, practice drawing your own. But this is just kind of an exercise to get you used to seeing what a unit cell might look like and why we use unit cells. It's better to draw a single unit cell than to have to draw this pattern across the whole page. Let's see, are we missing any questions? Yeah, I think drawing your own. All right, that's good enough for now. So, 10 minutes. Let's talk about coordination numbers. So, this is not something that is difficult because it is defined as the number of nearest neighbor atoms touching the central atom. So it's the same from that postulate. We're looking at how many atoms. So if you look at one atom in your structure, how many atoms are super close to it, like touching it? Things get a little bit more complicated when we talk about ionic compounds, but we'll come to that in a second. So coordination geometry, this is a way to describe the arrangement of those atoms. So if I have an atom in the center and I have 6 atoms around it, the coordination geometry, I can describe it as octahedral. But we'll get to those names in a little bit. So here's the one caveat to coordination number. If for a metal, when all the atoms are the same, then it's just how many, so take my one atom, how many atoms are near it, that's the coordination number. For an ionic compound, where you have alternating cations and anions, different atoms, we're only going to, so let's say my sodium is my central atom that I just picked randomly. I'm only going to count the chlorines around it, not other sodiums. So when you do coordination number, you have to do the opposite ion if you're doing an ionic compound. We'll get to that. We'll see examples of that soon. So I think the last thing I want to do is I'm going to build a 3x3 arrangement of pennies. And if I keep forgetting to bring pennies, but whatever. They look like this. Try to draw them the same size as best as I can.
We should have used our brass pennies.
Yeah, I know. Make that one better. There we go. So there's the pennies. If I put them in a 3x3 grid, they would look like that. What is the coordination number around that very central penny? What would you describe the coordination number be? Yeah, they're a little bit off size, but that's okay. All right. So, this is exactly what the last class had. It's fine. Even 50-50. The coordination number is going to be 4. So why 4? This central penny is closest to this penny here, this penny here, this penny here, and this penny here, and that's it. This penny is further away from these pennies. It's not as close. So nearest neighbor are going to be the atoms, or in this case pennies, that are as close as possible. Usually that means touching. Doesn't always, but sometimes usually means touching. So there's a coordination number 4 for this central penny, and that's it. And this is going to be a little tricky when you start looking at these three-dimensional structures, because you're going to really have to visualize what these three-dimensional structures look like. I'll have models, but you know, later on when you don't have the models in your quiz, you'll have to think about it. So if I were to describe what would I call the coordination geometry? I don't think we have a formal name, but if you had to describe it, what's the best description? Yeah, so looks like a square to me. So square is the answer in this case, okay? This is kind of just an example of coordination number and geometrical arrangement. Again, we're doing 2D. What we were going to do next, and we don't have time for it today, is start to do more math. We're going to calculate something called packing efficiency. So we'll start with 2D, which will expand to 3D afterwards. But we're going to look at, well, how tightly do they pack together? How much empty space do they leave when they pack a certain way? So if you look at this, there's a lot of empty space here. And we're going to give that a number. We're going to give it a percentage. How much of this unit cell here is filled with atoms and how much of it is empty? And believe it or not, we can use these numbers, the packing efficiency, and the mass of the atoms, and the number of atoms, and we can calculate a density. So we can physically calculate density by the arrangement of atoms, like physically at the atomic level. This is different from how we normally calculate density. What do? We take a bulk piece of metal, we weigh it, and then we measure its volume. Which is fine, that's the macroscopic way, but here we're doing the atomic way to calculate density. It's pretty interesting. And it works really well. It's pretty crazy. Yeah?
Is this nanostructure stuff going to be on the quiz next week?
No. We're going to stick with 24 to 20,
We're just trying to do that.
22 to 24. That's it.
Oh, okay.
Yeah.
And that's on
That's pretty cool.
Tuesday or
Thursday.
Thursday.
The quizzes are always going to be second lecture week. Yep. So Tuesday will be, say you turn in homework, any leftover questions and stuff like that. You know, if anything was difficult, you can ask them then. So that's it for today. We're going to continue with 24A on Tuesday. We'll do probably 24B as well. And then, yeah, we'll have a lab. Don't forget the lab stuff. Don't forget the mastering chemistry homework on Monday night. So the mastering chemistry homework on Monday night, there's two things due. There's a 221 review
Oh, yeah.
and a 22 to 24 kind of question stuff. And then there's the written homework. So there's a lot of homework. You gotta get used to looking up how to find them and doing them. All right. I'm happy to stay, answer questions. I think another class is coming in a few minutes, but
There was maybe a little eager like yesterday where they came in early.
yeah. That's normal.
No, I know. Just thought it was fun.
Everybody's excited. I mean, some of you guys, or not you, but some of you guys, it's your first college class in person ever.
Yeah,
You know,
sure.
so everybody's eager.